So I wanted to begin today's lesson by just going back to the simulation that you saw yesterday and pointing out a couple of details that you may have missed. Now I'm going to shift over to on the right hand side here, where I can see here I've got the material as air in the top space and I've got the material being water in the bottom space. Now I'm not sure if you happen to notice this little bit about this thing called the index of refraction, and that there's a numerical value there. And so air has an index of refraction of 1.00, and water has an index of refraction of 1.33. And so what we're going to be doing in this lesson is we're going to be learning a little bit about how to take what we know qualitatively about refraction when materials move from a less dense medium to a more dense medium or vice versa. And how do we make that quantitative? How do we make that, how do we use these indices of refraction as measurements of sorts? And what does all of that mean? So let's just take a look at a couple of things here. Well, I know that when light goes from air to water, that it's going to slow down, and that's going to cause my ray to bend towards the normal. I can see my angle of refraction here is going to be less than my angle of incidence, right? That ray is bending towards the normal. And so, but how does that relate to our index of refraction? Well, let's say I go ahead and I change my medium, the second medium, to glass, right? Well, I already know that glass is more dense than water. And so I'm going to expect that, this refracted ray is going to bend even more towards normal. But what is going to happen to my index of refraction? Let's see. Oh, my index of refraction all of a sudden went up to 1.50. All right, so it seems, I'm hoping that you're starting to make a connection between what the value of the index of the refraction is and what that means about the way that light is going to behave in it. So now that we've had a chance to kind of explore some ideas around the index of refraction, let's get a few notes down. Okay, so first of all, what is that index of refraction as we know it? It's basically a value, a numerical value that essentially will describe the relationship between the speed of light, so how fast light is traveling in air versus in that material. And it essentially is a ratio. So for instance, when we saw that glass had a value of 1.50, that has a meaning about how fast light's going to travel through that material. So we saw, hopefully, in the simulation, you were able to kind of make some connections and saw that the larger the index of refraction, what's the word that goes here? Blank the speed of light through that medium. The slower the speed of light through that medium. And we saw that with glass, right? So in air, the index of refraction was 1.00. Whereas in glass it was 1.50. So that larger index of refraction is going to indicate that light's going to travel more slowly through that material. So this is how we would interpret that value for the index of refraction for glass. So if we read that a particular glass has an index of refraction of 1.50, then what does that mean? Well, it means that the speed of light is going to be 1.5 times faster in a vacuum than it is in glass. Now, what do we mean by vacuum? We don't mean a vacuum cleaner. We mean in the vacuum of space, in the emptiness of space. So it's going to travel 1.5 times faster in space in comparison to in that glass. Now, I should mention to you that we are, like I said, going to be taking our knowledge of refraction and quantifying it. And some of you may be thinking, well, why do we really care about this? Why does this matter? Well, I'm going to, one example that comes to mind, I was watching forensic files the other day, and they were actually able to identify evidence at a crime based on the index of refraction of glass shards found at the scene of a crime. So that allowed them to connect it to a particular model of vehicle and so on, and then apprehend a suspect, which is pretty cool. So there are definitely applications for this. If you're interested in materials engineering, then understanding the refractive index of different transparent materials would be potentially super important depending on your field. So the beautiful thing is that, you know, people have done the work, and there is a data table that you can find, multiple data tables on the internet, but this particular one is located in your textbook. It's here for you, but there's also a text section in your textbook where you can find the index of refraction for a bunch of different media. So this is not something that you need to memorize by any means, but it may help you in some of the problem solving that we're going to do today. So for instance, here we see that if the medium is air or in a vacuum, then that is the lowest value for the index of refraction that we can see. And then light's going to travel more slowly in all other media, right? And so as we go down the list, and we see an increasing value for this index of refraction, right? We can see that the materials are becoming increasingly more dense, with diamond being at the bottom of that list with an extremely high index of refraction of 2.42. And that gives diamond some of its properties, right? The amount that light is going to be able to be slowed down and bent in a diamond has a big effect on how we perceive it to kind of reflect that light back, right? And we see a diamond as being sort of a very sparkly material. And that has very much to do with its high index of refraction, which is a function of its extreme hardness. Okay, so looking at calculations involving the index of refraction, we're first going to look at what is called the speed equation. And the speed equation, really what it does is it relates the index of refraction, which has the variable n, to the speed of light in a vacuum or in the emptiness of space, to the speed of light in that new medium. Okay, so like glass or ice or olive oil, etc. Okay, and so a couple of things that you're going to need to know is that the speed of light in a vacuum is always going to be 3.00 times 10 to the power of 8 meters per second. That is like a constant, and so that's just something we're going to be able to use in our problem solving today. So what I want to do is I'm going to switch to a Jamboard, and so I can work through some examples with you. Hopefully you've had the chance to write down this equation and the meaning of its variables so that you can start to think about how we might solve some problems using the index of refraction. Okay, so I'm going to remind you again that we want to try to adopt a good structure to our problem solving. So we're going to employ that GRASS method or a modified GRASS method, where we're going to just read through the question and start to draw out some of our givens so that we can select the appropriate tool to solve in this case. So let me read out this question. It says, calculate the speed of light in diamond. Okay, so let's pull out some material, some givens from this question. Okay, so first of all, I'm asking for the speed of light in a diamond. Okay, and so in this case, I'm going to remember that let's just remind ourselves of the equation. N is equal to C over V. Right? And so I'm going to need to know 2 out of these 3 things, N, C, and V. And so the index of refraction I can always find on a table unless I, don't know the material. The index of refraction in this case, I'm looking for the value for a diamond. So I just need to look on my chart, and there it is for diamond. So I can fill that in as a given. 2.42. And so C, you'll remember, is always the speed of light in a given material. And so that is always going to be 3.00 times 10 to the power of 8 meters per second. Okay, and so the question itself is saying to me, calculate the speed of light in a diamond. Well, that is my unknown. That's my required to find in this case. So V is what I don't know. Okay, and so when I look at my formula, the tool that I've chosen, If I'm finding out v, then I need to have c, which I do, and I need to have n, which I do. And so I'm going to go ahead and I'm going to just start to and substitute in my knowns into this formula. So n is 2.42. C, in this case, is, and always, is 3.00 times 10 to the power of 8. And then V is my unknown. Okay, and so I'm just going to manipulate this equation by cross-multiplying and then solving. But I'm also going to help you with this a little bit because, you know, we are doing virtual learning. And so I'm going to set you up with a nice little triangle, you know, the math equation or the math triangle that helps you solve things, right? So, you know, here we go. So if you'll remember this hopefully from density. So the way that this would work is n is here, c is here, and v is here. And so if I'm looking to solve for v, which in this case I am solving for v, then the equation would rearrange to c divided by n. I just kind of hide the v, right? And kind of, if v is what I'm looking for, then I would have c divided by v. So let's go ahead and do that. So, you know, I can use algebra to rearrange this, or I can simply rearrange the equation using my triangle, whatever works. But I'm going to get that v is equal to c over n, so 3.00 times 10 to the power of 8 meters per second divided by 2.42. And I'm just going to take a minute to calculate that. And the value that I'm getting, the raw one, is like this 1,2,3,966,942. And of course, that is a big, long number that, you know, in science doesn't really make sense based on the number of significant digits in my original values here. And so I'm just going to rewrite that in scientific notation, putting my decimal place between the 1 and the 2 and rounding that. So I'm going to get rid of that nasty one. And then my value when I round that will be 1.24 times 10 to the power of 1, 2, 3, 4, 5, 6, 7, 8 meters per second. So the last thing I want to do, because it's just good form, is just give myself a therefore statement and say, therefore, the speed of light in diamond is, and then it's the 1.24 times 10 to the power of 8 meters per second. And I'm done. Okay, so we've done one problem now. I want us to take a look at a second one, and I'm going to get you to maybe give this a whirl on your own and see if you can do it. So let's read through this question together. Okay, it reads, the speed of light in a solid is 2.29 meters times 10 to the power of 8 meters per second. Calculate the index of refraction to identify the solid. Okay, so pause the video now and give the question a try. All right, so I'm going to take this question up. And so I'm just going to take a look at my question and see what information is given. Okay, it says the speed of light in a solid is this value. That is my V. That's the speed of light in that material. So I'm going to write that out. V is equal to 2.29 times 10 to the power of 8 meters per second. Now, I always know what C is. C is always going to be the speed of light in a vacuum, which is 3.00 times 10 to the power of 8 meters per second. That's always a given, right? And so it asks me to find out the index of refraction. Okay, so it says calculate the index of refraction to identify the solid. So that's what's telling me that, you know, n is my unknown. That is my required to find. So I'm going to go ahead and I'm going to solve. I'm going to do that. So the tool that I'm using in this case is n is equal to c over v, because I'm given speeds in this case. And so just substituting in my known values, 3.00 times 10 to the power of 8 divided by 2.29 times 10 to the power of 8. And so working those values out, I get 1.31. And so then what I'm going to do is I'm going to look at my handy dandy table and I'm going to look for 1.31. Well, here is 1.31. So that allows me to make the final statement that since n is equal to 1.31, the material is ice. Hopefully you did okay with that question. There'll be more practice for you in your textbook for you to work through problems like this, and certainly reach out if you have any challenges. Okay, we are ready to go ahead and take a look at the second of two equations relating to the index of refraction. So the second equation that we're going to look at today is called the angle equation. So it may be that you don't have information about the speed of light traveling from one medium to the other. Maybe information that you're given relates to the angles, right? So for instance, the angle of incidence. So you might want to be able to predict, if you know the index of refraction, you might want to say, well, if I launch an incident ray at a particular surface at a given angle, how can I expect it to refract? What is that angle of refraction going to be? And not just sort of like in general terms, like away from or towards the normal, but an actual number of degrees. So those of you that were in grade 10 academic science with me will remember that trigonometry function, like the sine, cos, and tan trigonometric functions, we're simply going to be using those functions to solve today. So you will need to have a calculator with the sine function on it, and your iPhone, if you turn it sideways so that it has like a landscape form, the calculator should be able to show you a sine function there. All right, and if you don't have a phone, then definitely on your Chromebook, if you search up a scientific calculator, you should be able to find that. Okay, so when we look at this, n has the same meaning as before, the index of refraction. If we say the sine of angle I, we're talking about the angle of incidence, and we're dividing that by the sine of angle capital R, and that capital R meaning not the angle of reflection, but the angle of refraction. Okay, let's give some questions a try. Okay, so the first question here reads, calculate the index of refraction for material if an incident ray strikes the material at an angle of 48 degrees from the normal and causes it to refract 25 degrees from the normal. Okay, so let's start like we always should by writing out some givens. Okay, and so it says calculate the index of refraction. So that is telling me that my unknown is n. And that's what I'm trying to find out. But I know that my incident ray is striking the material at an angle of 48 degrees. So that tells me that I, in this case, is 48 degrees. But then that light is going on and it is refracting 25 degrees from the normal. And just remember that the angles are always measured relative to the normal, not relative to the surface. And so finally, I have my angle of refraction at 25 degrees. And it may help you to just write in that angle there, just to remind yourself that I and R are actually angles that you're inputting. So let's grab the tool. Now, I would say, we have two equations so far. I just want to have just a brief conversation about choosing the right tool. So I have two equations that allow me to solve for the index of refraction, right? These two guys that I'm writing right up here in the upper right-hand corner. Now, if I want to solve for the index of refraction using this first formula, I need to have speed values. But if I want to solve it using angles, then I need to have angle values. So basically, if I'm given angles, then I need to use the angle equation. And that's what I'm going to do in this case. So n is equal to sine of I over sine of capital R. So that means that I'm going to take the sine of angle 48 degrees and divide that by the sine of angle 25 degrees. Now here's where I want you to make sure that your calculator is in degree mode. So in case you've forgotten, what you're looking for is, you're going to be looking for that DEG or a D in your calculator. You'll remember that from trigonometry, and usually there's a button, a mode button like DRG that will allow you to toggle between degrees, radians, and gradients. So make sure your calculator is in degree mode. So if you're not getting the same answer as I am, that may be partly the reason. Okay, so now let me get rid of that. Boom. So now your calculator is either a forward calculator or a reverse calculator, and you're going to know based on, how you need to type this in. So some of you will need to type in, the 48 degrees first, and then the sign, and then maybe an equals. And others of you will just type in sine first and then 48 and then go from there. So you have to be comfortable with your own calculator. And so what you're, the math here, the inputting of it is really what I think the hard part is in this particular case. And so just go through the motions of typing it in to make sure you're getting the same answer as I am. And if you're not getting the same answer, then make sure to reach out via Zoom or check to see that you're in degree mode. And we can definitely easily sort this out. So I'm just going to go ahead and input this into my calculator. So sine 48 divided by sine 25. The iPhones, by the way, are the backwards calculators. I'm getting 1.75. So I'm just going to double check that. And I'm actually going to correct that because when I round, it should be 1.76. So hopefully you did okay with that. If you weren't able to get that answer, then it could be because you are in degree mode or in the wrong mode. All right, so let's try another question. And in this next question, I'm going to be asking you to solve for an unknown angle instead, which is, you might have to reach back to grade 10 trig to help you figure this one out. Okay, so in this question, it reads, an incident light ray hits a piece of ice at an angle of 45 degrees. What is the angle of refraction? Okay, so let's pause the video for a minute, and what I'd like you to do is just give it a try to write out your givens in this question. See if you can draw out the givens from the question, and then we'll take it up together. Okay, so let's take a look at this. Now, the question reads, an incident light ray hits a piece of ice. Okay, I'm going to leave that for a second, but the fact that it's telling us that it's a piece of ice will give us information about the index of refraction. And it hits it at an angle of 45, right? So that 45 degrees there, that is my angle of incidence. So my angle of incidence is 45 degrees. Now, the question reads, what is the angle of refraction? So that tells me that my unknown is big R. That is what I don't know. So that's going to make this question a little bit trickier. And so the last piece I need to know, therefore, because again, my tool is going to be using the angle function, the angle equation, sine of I over sine of R, which means that I need to be able to get, I need to have N as well. Well, how do I know what N is? Well, they tell me this is where ice comes in. Ice is my material, so therefore I'm going to look for the index of refraction for ice on my handy dandy table, and it's 1.31. And so now I have all of my information. Okay, so now I'm going to help us out again by creating a bit of a triangle to help you solve this. So just as we did for the index of refraction, here's a handy dandy triangle to help you solve for an unknown if N is not the unknown. It'll help you rearrange that equation. So the triangle would look like this. I would have N here, and then sine of angle I here, and then sine of angle big R here, right? And so again, if we have, this line right here means that I'm dividing, right? But if they're side by side, then that means multiply. So for instance, in this case, I want to get sine R all by itself, which means that I'm going to rewrite this equation as sine of R is equal to sine of I divided by n. Okay, so it's almost like I'm just sort of hiding this and then seeing the arrangement of what is left over. Okay, and so now let's input the information that we have. So sine of I, that means the sine of 45 degrees in this case, divided by n, which happens to be 1.31. Okay, now remember that this is giving us just the sine of big R. It's not actually going to give us R. And so what I'm gonna do is I'm just gonna erase this little triangle here because I know I'm gonna need a little bit more space. So what I'm gonna figure out right now is what the sine of R is by just inputting the information in my calculator. So you should do the same, and then we'll check our answers together. So here we go. Sine of 45 divided by 1.31. And I'm going to write that down to 3 significant digits, but I'm getting 0.540 when I round. Let me rewrite that. Okay, now you'll remember that in order to solve for an unknown angle, like angle R in this case, I have to use the sine to the -1 button. And so the sine to the -1 button is going to be located as a second function on top of your sine button. So just in case you're wondering about where that is, I've pulled up the question or the calculator again. Here it is just on top right here of the sine function. So you'll probably have to press shift or second function to get to that sine to the -1. All right, so back to our problem. And so really to solve for that unknown angle, I'm going to say, all right, well, sine, angle R is going to be equal to sine to the -1 of 0.540. And so you should still have that 0.540 in your calculator, and all you're going to do is press second function sine usually. And if I'm rounding that to the nearest degree, I'm getting 33 degrees. And so, to finish this off, I would say, therefore, the angle of refraction is 33 degrees. Now, we should also make sense of this. So, I'm just going to go ahead over here, get rid of, and then let's draw this out. Let's make sense of this. So if I have 2 media, right, and remember that my first medium in this case was assumed to be air, right? So I have air here, or vacuum, and then I have ice, right? So if I draw in like I'm just going to kind of fake a normal line here. Here's my normal line, right? It's at a right angle to the surface. And if I have a light ray that's coming in at a 45-degree angle, right? And I said that was, here's my angle of incidence, so I equals 45, right? Well, I know that, moving from air into ice, I'm going from a less dense to a more dense material. I'm going to expect that light ray to bend towards the normal, right? And so in other words, I'm going to expect this angle R here to be lower than 45. Any answer that would be larger than 45 would mean that ray right there moved away from the normal. But it should be moving towards the normal. And so the fact that I get an angle of 33 degrees for my angle of refraction makes sense in this question. And so, so I can be confident in that answer. So just a reminder to just always try to think about whether your answer is reasonable or not before you decide that you're all done. All right, as always, there'll be some practice with this, but you can always reach out on our Zoom meetings daily to get some extra support, some one-on-one practice if you need that extra assistance.